It's a great pleasure to introduce Christiana Pantelidou, joining us today from UCD. Christiana received her PhD from Imperial College, and after that did postdocs at Barcelona University, Durham, and Trinity, before joining UCD as a Royal Society SFI Research Fellow. And her research covers various topics in gravity, including stability properties of black holes and relation to fluid dynamics, and many other topics. And today she's going to tell us about some very recent work. I think I saw the paper a couple days ago,
Tuesday,
on the archive on non-modal effects, transient superradiance. Please.
Thank you very much. Let me start by thanking the organizers for inviting me to speak, and Yosemite in particular. So today I'd like to tell you a little bit about some work that I've done recently with Javier Carballo and Benjamin Withers, both at the University of Southampton, that, as Yosemite said, appeared earlier this week on the archive, on non-modal effects in black hole physics, and specifically non-modal transient effects. And as you will see, hopefully later on in the talk, the mechanism that gives rise to this transience is very general. So in principle, we could see this effects in black holes in asymptotic flatness, or in de Sitter space-time asymptotics. But here, for the sake of simplicity, we're focusing on charge superradiance in ADS. And to some of you, this system might be better known as the holographic superconductor. But so just to emphasize, even though here we are dealing with ADS, the phenomenon is more general. So let me jump right in. The story today starts with a discussion about quasinormal modes. Okay, so as you all know, black hole quasinormal modes essentially control the response of a black hole to linearized perturbations. And these modes arise essentially as eigenmodes of the Hamiltonian of the system, if you want the evolution operator in the system. And over the last few decades, we have received a lot of attention in the literature, mainly because they contain intrinsic geometric information about the black hole. So essentially, you can use quasinormal modes to characterize your black holes. And because of that reason, they have found lots of applications in a variety of directions within gravitational physics, ranging, for example, from astrophysics. And in the last maybe 4 or 5 years, we have seen a resurgence in the so-called black hole spectroscopy program, where people are trying to extract quasinormal modes from gravitational wave signals from the ring down part of black hole mergers, in an attempt to extract information about the mass and the spin of the final black hole. But the quasinormal modes have also found applications in mathematical relativity, say when one wants to understand whether a certain formulation is well posed or not, more fundamental questions related to black hole stability, and last but not least, through the gauge-grounded correspondence, where these quasinormal modes essentially control and characterize the dual theory on the boundary of ADS. Now, all this comes with a big caveat, and the caveat is that the Hamiltonian operator that gives rise to these modes is actually a non-normal operator. And this non-normality simply comes from the fact that black holes have a horizon. So energy is allowed to dissipate through the horizon. Okay. If we are in asymptotic flatness, we also lose energy through the UV.
So what do you mean by a non-normal operator in general?
I'll show in the next slide. So, okay, the fact that the Hamiltonian is non-normal means that the spectral theorem does not apply. And if the spectral theorem does not apply, that has important consequences about the properties of the quasinormal mode themselves, and as a consequence of that, on the physical processes that we can have. And one of such consequences is precisely transience. So, okay, so what is the spectral theorem? So the spectral theorem says that if you have a system that is closed and non-dissipative, then the Hamiltonian of the system is a normal operator. And by normal, what I mean is that it commutes with its adjoint. Okay. So in order to define the adjoint, you need to introduce an inner product. Okay. So that's what a normal operator is. A non-normal operator is something that does not commute with its adjoint. So, so in systems where we do not have any sort of dissipation, the spectral theorem guarantees that the eigenvalues of such a system are stable against perturbations of the Hamiltonian, and that the eigenvectors of such an operator are orthogonal and complete. But on the other hand, when we are dealing with systems that are open or dissipative, such as black holes, then the Hamiltonian of the system is now non-normal, so the spectral theorem does not apply. And this has two important implications. First, in terms of the eigenvalues of the quasinormal mode frequencies, these are now complex in the systems, and they can potentially be unstable against perturbations of the Hamiltonian. And you should think of these perturbations as environmental effects affecting the system, or for example, internal uncertainties that you may have in your theory. So this is the first implication, potential spectral instability. And then the second implication is that the eigenvectors of the system are now neither complete nor orthogonal. And in this talk, we will precisely exploit this implication to see transients.
It just means that in the usual case, you've got left eigenvectors and right eigenvectors, and they can be different, even different dimension Hilbert spaces. So.
Sure, yeah. But it's a matter of understanding what the implications of that are. So in terms of black hole physics, not much attention has been given in this non-normality. And the attention that has been given in the literature was mostly focused on this implication here, in terms of the potential spectral instability. And the consensus on that is that black holes are spectrally unstable, and that's a universal result. It doesn't depend on the space-time asymptotics. And the first evidence for that actually go all the way back to the late 90s, to Noller and Price. But there was a revival, if you want, an extension of that line of research more recently, in 2021, by Jaramillo and his collaborators, where they imported the notion of the pseudospectrum from fluid dynamics in order to study this spectral instability. So this is established, the spectral instability is established. What is currently not well understood, at least not to my taste, is what are the physical implications of that spectral instability, especially in the black hole spectroscopy program. Now, having said all that, in this talk today, we are going to focus on the implications of non-normality on dynamical effects rather than quasinormal mode frequencies. And this, as I said, will give rise to transients. So what is the prototypical example where non-normality gives rise to transients? Well, it goes back to fluid dynamics, and more specifically to the study of turbulence in shear flows. Okay, so let's focus for a minute on the so-called plane Poisson flow, which you can think of in the following way. Just imagine you have two plates, two-dimensional infinite plates, like what you see here, and in between those two plates, you have a fluid with a certain viscosity that is flowing in this direction with a velocity profile that looks like a parabola. Like what you see there. This is what the plane Poisson flow is. Now, let's say that we want to study linearized perturbations around that configuration. What do? We take the Navier-Stokes equation that controls fluid dynamics, and we linearize around this configuration. And what we get is the so-called Or-Sommerfeld operator. Now, it's not difficult to show that this Or-Sommerfeld operator is in fact a non-normal operator with respect to the energy inner product. And we'll come back to this point in a minute. Okay, so given that we have this operator, the natural thing to do is to study its eigenvalues. And this is what we call a modal analysis. And what people found was actually that when the viscosity of the fluid is such that the Reynolds number is equal to this very large number here or larger, then the quasinormal mode spectrum has one quasinormal mode that's in the upper half plane on the frequency plane. So we have a runaway process, we have an instability. And this stability essentially takes you from a laminar flow, like what you have here, to a turbulent flow, like what you see here. So you have essentially vortices that are elongated and then propagate in this direction. Now, this is what the eigenvalue analysis said. And experimentalists tried to test this in the lab. And what they found was that actually the transition from laminar to turbulent starts much earlier, so from a much lower Reynolds number than the value you see there. And this had the community puzzled for quite a while, until Threfton and his collaborators came up with the so-called non-modal analysis, and I'll tell you more about that in a minute. And essentially using that analysis, they showed that one can have transient energy growth in the perturbations, and that energy growth was substantial enough to trigger turbulence at the nonlinear level. Okay. So the reason why turbulence sets in much earlier is because of transient effects. Okay. But what do we mean when we say non-modal analysis? So essentially people mean these two quantities that you see here, the growth curve and the optimal perturbation. So the growth curve is the maximum possible energy that we can store in the perturbation at any given time, tau. And the optimal perturbation or optimal initial data is the initial data that we should have for the perturbation, and in such a way to give maximal energy amplification at the target time, tau star. Okay. So this is what happens when you do model analysis for the plane Poisson flow that I showed on the previous slide, but for Reynolds number equal to 5,000, so much smaller than the critical Reynolds number. And here in black, you can see the energy growth curve, and the energy associated with the optimal initial data when you evolve it in time is given by this red dashed line, okay? And the target time was picked precisely at the value 18. That's why the two curves match at precisely that point. And what we see is precisely a transient behavior. So we see energy growth for short time scales. And by energy growth, we really have in this example by a factor of 30, which is quite large. And then later on, we see a modal decay as we would expect, since we're in the stable phase. We don't have a runaway process. Now here, the decay is very slow, so it might look like it's flat, but it's not. It decays. And just because this point will be important later on, the two curves, the growth curve and the energy associated with time evolution of the optimal perturbations are not the same. Is it clear what the difference is? So if I construct the optimal perturbations at different target times, then the peak of that curve will essentially trace out the black line, which is the growth curve. So the growth curve maximizes the energy at any given time across all possible initial data. Is that okay?
Yeah, I mean, you know, definitions of these things.
Yes.
Are defined, I can't tell but.
Okay, so this is the situation in turbulent flows. Turbulent flows in fluids, and this naturally brings the question, okay, so when we're dealing with black holes, we also have a non-normal operator. Can we see transient effects in that setup, just like we saw in fluids? Okay. And Javi and Ben started to address this question last summer. And in order to address this question, they did non-modal analysis for some very simple setups in black hole physics. Like, for example, they studied the BTC black hole, where we know quasinormal modes analytically, so they had a good control. But they also studied systems in asymptotic flatness and the Sitter boundary conditions, and pretty much they saw the same type of results. And this is what they saw. Once again, the black line here is the energy growth curve, and the dashed red line is the energy associated with the time evolution of optimal initial data targeted at roughly tau star equal to 9.
So what equations are you solving here? And you've got the Einstein equations and
yes, okay, so in this, yes, so here they consider a scalar field, a scalar field perturbation around the BTC black hole. So they were studying scalar quasinormal modes in BTC.
The Hamiltonian for this is the Hamiltonian depends on how you're going to section, or you're going to find
yes.
spatial section.
Yes,
size.
yes, you're way ahead. That's slide 15. I'll give all the details about the slicing and the inner product and all that, because if you are going to talk about non-normality, you also need to define the adjoint, and that requires an inner product. So, yeah. So here, the inner product I considered was the energy associated with the scalar field, which would be the natural.
But you only put and in what spatial sections?
Hyperboloidal. This calculation was in hyperboloidal.
Sections.
Yeah, I'll show.
You chose a general
yes. So this is the plot that they got, and here we see that at short time scales we see effects that are not modeled, which are we call transients, and then at later times we have dissipation according to the slowest quasinormal mode. Okay, so in this setup we see transients, but we do not see transient growth. And the reason for that is actually quite simple. So we only allow energy to flow out of the system. So best case scenario, the energy in the perturbation will either stay constant or it will decrease. So we couldn't possibly have energy growth in this setup. And this conclusion pretty much agrees with conclusions that people arrive to using the pseudospectrum. So I think this is fairly well understood. But this sort of calculation gave rise to a very interesting phenomenon that is delayed thermalization. So depending on the details of the calculation, you can make this plateau that you see here arbitrarily long, finite, but arbitrarily long, which means that your perturbation has a lifetime that it can be very large. Yeah, that's a very interesting phenomenon. What are the implications for thermalization in black holes or for the CFT side of things? That is an interesting question. But this takes me to the question that I want to address in this talk today, which is there any system in black hole physics where we can actually see energy growth? Okay. And the hypothesis that we have is that one can indeed see such energy growth when we are in the vicinity of black hole instabilities. And the mechanism that gives rise to this energy growth is that the perturbation is borrowing energy from the background configuration. So effectively, because of the coupling between the perturbation and the background, one can have this sort of effect. And if this is indeed the mechanism, just borrowing energy, shifting energy from one field to the other, then this is fairly generic. So this is what I was referring to at the very beginning, that the mechanism is very generic. So it shouldn't apply only in our specific case here. And as I was saying earlier, just for the sake of simplicity, we're focusing our attention on the holographic superconductor or equivalently charged superradiance in ADS. Okay. So any questions at this stage? No? Good. So let me give you now all the details. So as I said, we're focusing on the holographic superconductor in 4 dimensions. So the action that we're considering is this one. So we see the Einstein-Hilbert term with a negative cosmological constant. We see the Maxwell term. So here we have the field strength F associated with the gauge field A. And then we have a charged complex scalar field psi with charge Q with respect to the U1. And once we have this action at hand, we can go and compute equations of motion, and then we can start discussing solutions of those equations of motion. And the simplest such solution is the unit radius ADS4 with the gauge field and the scalar being completely trivial. And using the holographic dictionary, this solution is dual to a 3-dimensional conformal field theory with a conserved U1 current. So that's the simplest solution. And one level up in complication is the electrically charged ADS Raster-Nostrum black variant. So now we have a gauge field A that has a non-trivial profile outside the horizon. So we have an electric field in the bulk. But still, the scalar field is trivial everywhere. And this black hole configuration is now dual to the high temperature, homogeneous, and isotropic phase of the dual field theory when placed at a finite chemical potential. Now, at this stage, we can go and compute quasinormal modes for this electrically charged Dresden-Nostrum black hole. And what we'll find is that if we keep reducing the temperature, at some point there will be a quasinormal mode that will move in the upper half plane, so it will become unstable.
So in anti-de Sitter space, there are small black holes and large black holes. So when you're talking about what is the you're presumably talking about small black holes, because you want to spot a positive specific heat. Okay, all right.
Yes, so we have one quasinormal mode that is now in the upper half plane, and that signals an instability. And this instability is towards the formation of scalar hair. Okay. So for temperatures below a critical temperature, we can go and construct numerically black holes that have not only a non-trivial gauge field, but also a non-trivial scalar field. And on the dual field theory side, this would correspond to the superfluid phase. So in what comes next, we will we'll focus on the electrically charged Dresden-Nostrum black hole, and we'll do a modal analysis and a non-modal analysis for temperatures mostly slightly above the critical temperature. And that regime I will call subcritical, and then I'll make one small comment at the very end about what happens if you do a non-modal analysis in the supercritical regime. So when the temperature is below the critical one, so you're on the unstable branch. Okay, but going back to Denja's question, how am I foliating? What coordinates am I using? So here we're just following the trend in the literature to use hyperboloidal coordinates. So we are foliating our space-time using space-like surfaces that pierce the future horizon. Now, the reason we choose these coordinates is because on these slices, which I call capital sigma tau, the quasinormal mode functions are regular. This is not the case when we're dealing with Poincare coordinates, for example. So in Poincare coordinates, we have the functions are irregular. Yeah, it's more difficult to impose ingoing boundary conditions in those cases.
Just to understand you, Daniel, where is the boundary Where should I understand the boundary of ADS?
So the boundary of ADS is here,
Okay.
and this is the future horizon. So essentially, these slices, they behave very much like ingoing coordinates close to the horizon, but they deviate closer to the boundary. So yeah, if you want, it's something in between ingoing coordinates close to the horizon and then Poincare closer to infinity. At the practical level, how do you go to hyperboloidal coordinates? Well, it's a simple coordinate transformation. From T and R Poincare coordinates, you go to hyperboloidal time tau and z using this coordinate transformation. So T is related to tau using this function h of z, which is referred to as the height function. This is a known function. I just didn't write it down for simplicity. And then the radial coordinate in the bulk of ADS is related to this coordinate z through this function, but typically what we use is r is equal to 1/z. Okay, so the boundary of ADS is at z equals 0, and the horizon is at z equal 1.
Okay. So which picture is then the right? Which coordinate system? This one here is?
These are the sigma tau.
Sigma tau
coordinates.
coordinates. Okay.
So these are constant hyperboloidal time slices. Okay, so with these coordinates, we can now go back to the equation of motion of our scalar field that looks something like this and massage it down to bring it to a more familiar form for when we talk about the Hamiltonian of the system. And in order to do that, we need to do a time reduction. This equation here has second time derivatives. And in order to write it in this way, we need to reduce down to only one time derivative. And we do this by introducing this vector here, psi and psi derivative. Okay.
And you've got the lapse and shift here or something?
Yes, so the Hamiltonian of the system, the evolution operator is this curly H.
Yes.
Which is now a 2x2 matrix of operators. And L1 are operators themselves, and they include powers of z and first derivatives with respect to z and second derivatives.
The lapse, you're not shifting as you want. Is that what it means? There's usually, when I foliate, I'm going to have a lapse and a shift. I mean, there's a normal vector to your foliation, and you're choosing, you have a choice in the Hamiltonian as to how would we foliate, which is because you've got to a first order form. It's probably one, yeah, you've probably chosen unit vectors.
Yeah.
Okay.
Okay, sure. So this is the Hamiltonian that describes the evolution of this scalar field, and it has these two operators. It's built out of these two operators that have powers of z and derivatives with respect to z, and it's not too difficult to see that information about the leaking information about the horizon essentially is included in this L2 operator. So the fact that this guy is not normal essentially can be tracked down to L2. Okay, so those are the coordinates that we're using. Now I also need to specify for you the inner product that we want to use. And the natural choice here is to consider the energy, the inner product that is derived from the energy of the scalar field. So the energy of the scalar field is simply given by the scalar stress tensor when integrated on those spatial slices. And here is the normal vector to the that slice. And then we can try and understand what are the properties of this guy, and in particular, whether it's conserved or not. And as you would imagine, it's not conserved. And it's not conserved in this precise form that you see here. So it has one term that essentially gives us the flux of energy through the horizon. And then we have another term here that essentially is a manifestation of the interaction between the scalar field and the gauge field. Okay? And as we will see later, it's precisely because of this term that you can move energy from the scalar, from the electric field or the gauge field to the scalar. Okay, so now having this energy at hand, we can go and define the inner product. The inner product is a bilinear, so it takes in two functions, psi1 and psi2, and it constructs the inner product in this way through the so-called Gram matrix, which I denote by G tilde. And G tilde, G curly G, is essentially fixed by the requirement that the energy, that the inner product, when psi1 is equal to psi2 equal to psi, should simply give the energy stored in the scalar field if psi was the profile of the field. Okay, so this is the energy inner product that we'll be interested in. Okay. So I think at this stage, we have all the machinery that we need, at least for the model analysis. So what do we have if we try to study the spectrum of the system? So here on the left, I'm showing, I'm focusing my attention, as I said earlier, on the stable branch, so slightly above the critical temperature. And here I'm plotting the quasinormal modes on the complex frequency plane. And we see that all the modes are in the lower half plane, which simply means that we are still on the stable branch. Okay. And as you can see, we have three branches of quasinormal modes. And just for later convenience, let me introduce the notation that the eigenfunctions are denoted by psi n, and the quasinormal mode frequencies by omega n. But if these quasinormal modes do indeed come from a Hamiltonian that is non-normal, then the lack of spectral theorem tells us that these quasinormal modes should not be orthogonal amongst themselves. And given that we have already defined an inner product, we can just go and check. And this is what is shown here on the right-hand side. So here I'm taking the inner product between psi I and psi j, so quasinormal mode I and quasinormal mode j, and I plot it as a function of I and j. So if I and j is equal, then we are on the diagonal, and this inner product is equal to 1 because we chose to normalize it that way. But as I minus j increases, so as we are moving in this direction or in that direction, from white it goes to gray and more gray and deeper gray. It never becomes black. So what this means is that this inner product here, it becomes smaller and smaller. So the modes become more and more orthogonal as we move towards the side, but they never actually become zero. Okay, so this is essentially a check that indeed the Hamiltonian of the system is not normal. And interesting, I don't know if you can see it, but there is a pattern here in terms of the overlap, and that is just a reflection of the fact that on the left-hand side we have three branches, and the three branches have different orthogonality properties amongst themselves. Okay, so this is the model analysis. Now we want to do a non-modal analysis on top of that. So here we want to compute, as I said earlier, the growth curve and the optimal perturbations. And this is the algorithm of how to do it. So the first step, which is essentially what we did on the previous slide, is to construct quasinormal modes, psi n, omega n, as a function of the set, and then order them such that, order them in terms of the smallest imaginary part of their frequency. That's the first step. The second step is to restrict ourselves to the first n such modes. So by doing that, we're essentially restricting ourselves to a subspace of the functional space. Okay, So we're restricting ourselves to a subspace W. Okay, and then on top of that, we choose to normalize these modes with respect to the energy norm. So now we have psi tilde and omega n. Okay. The third step is actually to use Gram-Schmidt and introduce an orthonormal basis within this subspace W. Okay, and I'll denote that by Z and omega n. And in the process of doing Gram-Schmidt, we get this this matrix U subscript W that is an upper triangular matrix, and that's essentially the change of basis matrix. Okay. And then so now we have two bases, essentially the original one normalized and this orthonormal one. Okay. So the next step, step 4, is to actually compute the Hamiltonian in this orthonormal basis. And to do it, we essentially start from W, which is a diagonal m by m matrix with the quasinormal mode frequencies on the diagonal, and then sandwich that with u to the -1. Okay. So HW is the Hamiltonian in the orthonormal basis within the subspace W. And these are all the ingredients that we actually need. Computing the growth curve and the optimal initial data is essentially singular value decomposition of the evolution operator that you see here. But let me elaborate on that. So the growth curve restricted to the subspace W is essentially, as I said earlier, the maximum energy you can have in the scalar field appropriately normalized when optimizing in terms of all possible initial data that I can have in the subspace W. And this is not too difficult to show, that is equal to the energy norm of the evolution operator in the original basis, which in turn is equal to the 2 norm now of the evolution operator with the Hamiltonian now in the orthonormal basis. Okay, so essentially we plug in different values for tau here. We do a singular value decomposition, and out of that singular value decomposition, we pick out the maximum singular value, and that will give us the growth curve at the given tau that we picked. And then if we give several values of tau, we get those plots that we saw earlier.
So you didn't really need to do that Gram-Schmidt process there. You could have just worked with the truncated Hamiltonian and taken the single values H. You now have a matrix, you can take H dagger H in that finite one, and you can find its diagonal values, those with singular values.
I'm not sure about that, because here we are doing the energy norm. So the benefit of going from the original basis to the orthonormal basis is that this is a simple 2 norm. And maybe there is a way to do it.
Well, if they're singular values, if you're using the standard definition of singular values, then you could have gone through it the way I'm saying. I presume you are.
Yes, but you have to be careful with the norm you're using. So if you want something,
you're truncating it, you shouldn't have to. If you're just going
no, the truncation is one thing, and the inner product that you chose is a different thing. So here, if you take the Gram matrix that I showed earlier, then you can do some sort of Cholesky decomposition. So write that as F star times F, and take that into account here, and then that would convert the energy norm to the 2 norm, but you're effectively doing something very similar. Yes, so that's what one does for the energy growth curve. For the optimal equation, once again, it's just a simple singular value. So in order to get the optimal initial data, given that we have the orthonormal basis, this reduces to just finding the coefficients dn in the sum. And it turns out that these coefficients are simply given by the right principal vector of the singular value decomposition of this guy here. Okay. But of course, given that we have the change of basis matrix that we saw on the previous slide, we can convert from the orthonormal basis back to the original basis, and that will relate the coefficients dn to this coefficients cn in terms of the original basis. But the point here is that the optimal initial data that we're dealing with are not single quasinormal mode. It's a sum of quasinormal modes. And it's precisely this, the fact that it's a sum of quasinormal modes, and in the original basis, those quasinormal modes do not overlap, are not orthogonal to each other. That's what gives rise to the phenomenon that we're interested in. So,
is there restrictions on how to choose the n number?
In principle, it's a choice, and I'll come back to that. So if you have a very large m, then your initial data might be a bit fine-tuned. So you want it large enough to have big enough energy growth, but you don't want it to be too large, because then you're fine-tuning things a bit too much.
And not too small.
And not too small, yeah, because then the growth you achieve is not much. But I'll back that up with a couple of plots in a minute. So let me show you what we got when we did the non-modal analysis for the subcritical region. So we're still on the stable branch. And here, the black dotted line is the energy growth curve, and the black solid line is the energy of the time evolved optimal initial data when targeted at 9.8. Okay, so the point here is that for short time scales, we see an energy growth. And that energy growth is followed by model decay, as you would expect, given that your system is on the stable branch. So we see a clear indication of transient energy growth. Now, in the with the green line here, you see the charge that is localized outside the horizon. So essentially, the charge that is carried by the scalar field. So it's not surprising that this line pretty much follows the black line. Okay, and actually, I should have said that for this plot here, we have used m is 10, and the amplification that we managed to get was a factor of 6. Okay. So this green curve here, the charge outside the horizon, pretty much gives us a clue as to what physical process is happening in the background. And that physical process is that because we have the electric field in the bulk, that electric field essentially gives rise to transient pair creation. So you have positively and negatively charged particles that are forming in the bulk. The negatively charged are absorbed by the black hole. So you have only the positively charged forming some sort of transient cloud outside the black hole. Now, this is not a sustained process. So eventually everything will fall fall back in. Okay.
You're not taking back reaction.
No, everything is linear. But non-linear effects will be very interesting to study. So, okay, and this also hints as to the mechanism that we have here in play. So we have transfer of energy from the gauge field, so from the electric field to the scalar field momentarily, and then that goes back to the scalar field, to the gauge field. And this is why I was saying earlier, this seems to be a fairly generic mechanism. And some of you may have noticed several similarities between this black hole setup and the fluids that I was talking about earlier. So here we have a pair creation of positively and negatively charged particles. In the other case, we had oppositely moving momentum modes, and this is essentially what gave rise to the vortices. And in this case, the scalar cloud is breaking a U1 symmetry. In the other case, there was a breaking, but of translations. And here we have moving energy from the electric field to the scalar field. Back in the fluids case, we have transfer of energy from the mean flow, so the parabola that we had in the background, to the perturbations. So there are many similarities between the two cases. Of course, there are differences also. And the biggest difference is that in the black hole case, the loss of energy happens through the boundary, the horizon in this case. While in the case of the fluids, it was a bulk effect. It was through the viscosity. But overall, there are many similarities in terms of the phenomenology. Okay, so you may now wonder, how do the actual optimal perturbations look like? And here I'm focusing on the same case as before, same temperature. So we are still in the stable branch, m is equal to 10. And here I'm plotting those coefficients d, n, and cn that I showed earlier. So in the orthonormal basis, those coefficients are pretty much order 1. And if we go to the original basis, those coefficients look huge. And so it would appear that if we were only to consider the original basis, this optimal perturbation would appear very fine-tuned. But actually, if you think about it in terms of the orthonormal basis, it's really not. Okay, and with these coefficients at hand, we can then multiply with the appropriate basis, and we can construct the profile of the initial data, and then we can time evolve. Everything we do is linear, so the evolution is simply by multiplying with e to the minus I omega t. And this is the profile that we get for the scalar field when we take out some powers of z. And what you see here, this is the hyperboloidal time tau, and this is the bulk direction. So if we're at very small hyperboloidal time, we see that the scalar field is very much localized close to the horizon. And for a little bit of time, it does stay localized there, and only later on, it actually starts to diffuse towards the bulk. And now that we have this scalar field, we can go and compute its energy density. And we see something very similar. So we have the energy in the scalar field localized close to the horizon, and it stays there for a little bit. So it's like having a wave packet that is propagating along the horizon without interacting with anything. And then eventually, after a bit of time, it starts to diffuse. This is very similar to what Ben and Javi saw last year with that plateau. So something stays, the energy stays pretty much unchanged close to the horizon, and later on it sort of interacts with the rest of the space-time. And now let me come back to your question. So what happens if we increase m? So earlier, I showed plots for m is equal to 10, and the amplification factor was roughly 6. If we keep including more and more modes, then the maximum on the growth curve actually increases. We only checked up to 70, and up to there, it seems to grow. It seems to keep growing. Now, we don't know if that growth will eventually plateau or not. But that might be important for seeding nonlinearities. But having said that, as we increase the value of m, we see that the initial perturbation is more and more peak close to the horizon. So probably you can't really see that well, but the blue solid line is for m is 10, and the sort of orange line is for m is 70, and you see that the orange curve is picked much closer to the horizon. So there is this question of how much amplification you want and how much fine-tuning you're willing to do. So the punchline from the last couple of slides is that in black hole physics, we do see transient energy growth, just like in the fluids. And as I tried to point out to earlier, the reason why we get this mathematically is because of the non-orthogonality of modes. And just to emphasize that a little bit more, let us study what happens to the energy of the scalar field and the time derivative of that energy for a single quasinormal mode and for a sum of two quasinormal modes.
Before you do that, if I go to arbitrarily high energies, I'm going to Schachter to find a structure in the quasi-normal modes, I should be able to say exactly analytically what's happening for the shortest modes. The Hamiltonian there should be
in principle, yes. Yeah.
So you expect that they will become orthonormal. I would imagine.
Yeah, maybe. Maybe you give me more details. So what I do know is that we maybe be able, for very large value of m, to get the behavior of that line analytically, which we haven't done.
The highest frequency, I would think you should be able to analyze because you know the structure of your Hamiltonian.
Yeah.
And you should be able to get it out from.
Yes.
It's presumably a hyperbolic operator.
Yeah.
So you can get it from the leading symbol.
Yeah, in principle, we could do that. We can extract what probably this line would go to.
I would think you should.
Yeah. But you see, do we have to do that?
No,
no.
It tells you if you know that it's lower than this.
Yes, absolutely. But what I was trying to say is that if this amplification that we already see here, say for 50 modes, if that's enough to sit nonlinearities, then we don't need to go to higher values of m.
It depends on what you're looking for,
I suppose, yes. Okay, so I was trying to make an argument why this phenomenon is attributed to non-orthogonality. And I was saying that we should focus for a moment on the energy in the scalar field and the time derivative of that energy for a single mode and for just a simple sum of two quasinormal modes. So if we do this, I gave you earlier the expressions for the energy of the scalar and the time derivative. So if we take those expressions and we plug in the behavior of a single quasinormal mode, this is what we get, where omega here is the frequency of that quasinormal mode, and this quantity here is the amplitude of the mode at the horizon. Okay, so we get an expression like this. So demanding that this time derivative is positive gives us precisely the Superradiance condition. Okay, so this is just an alternative way of deriving those conditions that typically people get by thinking in terms of scattering. So I send in a wave, what are the conditions so that the wave that comes back has more energy than the initial one. This is just a different approach. But if we now consider two modes, and with frequency omega 1 and omega 2, and amplitudes z1 and z2 at the horizon, we get three terms, not two terms. So this term and this term are precisely what you expect from this calculation, but we have this extra term here that essentially controls, it's there because of the non-orthogonality of the two quasinormal modes. Okay, so even if this term and this term are such that the derivative of the energy is negative, so we are in the stable branch, this term here opens the door for transients. So essentially, this might be bigger than the sum of the other two terms. So yeah, effectively, the transients that we see are a result of non-orthogonality. So just a small comment about non-modal analysis in the supercritical regime. So here we are at temperatures below the critical one, and in principle, and by definition, we have a runaway process. So we have a quasinormal mode in the upper half plane, and the energy of that mode is increasing. And the question then is, can we have a configuration, an initial perturbation, such that the energy growth is faster than model, even in the supercritical regime? And the answer is yes. Okay, so here I'm plotting the optimal perturbations, and this the dashed blue line is essentially the model behavior. Okay? So we see that even in the supercritical regime, we can arrange for a situation in which the energy of the scalar field grows much faster than modeling. And with that, let me just summarize and conclude. So here we studied non-modal effects in black holes, and when we're in the vicinity of black hole phase transitions. And what we saw was that indeed we can have energy growth in a transient fashion. So in short timescales, we have energy growth, and then that is followed by decay according to the slowest quasinormal mode, and that energy growth can be large. Okay, and then the phenomenology of these non-modal transients that we saw very much mimics what happens in turbulence. In terms of future directions, there are many. One of them has to do with the origin of this instability, and I think this relates to what you were saying earlier, Angel. So the holographic superconductor has been understood as a Swinger pair production in the vicinity of ADS2. So do the transients that we see also are also rooted in ADS2 physics. That's one direction. The other one has to do a little bit with the fine-tuning, and we have some preliminary results in which we did not start with an optimal perturbation. We just started with a Gaussian that was peaked very close to the horizon. And then we did the time evolution, and we saw behavior very similar to the optimal perturbations. So this hints towards the fact that there is no tremendous amount of fine-tuning here. But with the caveat that then your amplification factor is slightly smaller. In terms of nonlinearities, is the growth that we see here enough to see nonlinear effects? And if that is the case, then what sort of phases do you get? What sort of situations do you find yourself in? Will it be some sort of, will it thermalize, will it not? So in principle, we expect to see some novel states in the dual field theory, but the question also arises in black holes. What sort of black hole configuration do you have? And last but not least, there are lots of connections with other types of physics. Remember, I did try to emphasize that we have an energy wave packet that is essentially, for quite some time, it travels parallel to the horizon of the black hole. That resembles a little bit the Arrhidakis instability. Then in terms of the delayed thermalization that I talked about earlier, one can show that that plateau that I showed earlier is proportional to log m, and that is scrambling time. So are there connections with scrambling? And there are also questions about how this type of work may be pushed to the nonlinear level. How does that relate to the ADS instability? So there are lots of open directions. And with that, let me thank you and stop talking. Yeah.
So you were saying about how the energy transfers between the scalar field and the gauge field, and then is eventually lost. How do you?
Well, it's not lost. It just
Yeah,
goes back to the
just
electric field.
so it just goes back. So do you have like a handle on where it is in the electric field? I mean, is that something that you see, or is it just because it can't possibly come from anywhere else?
You can actually you can compute the electric
Compute it,
field.
you could just calculate it, and you can see exactly that it's in. Okay.
Can I go in a slightly different direction?
Yeah.
Just
Yeah.
because I want to understand a little bit better
Yes.
about the relation with the dual picture.
Yes. I'm not sure there is much there to understand.
No, you're
Yes.
making an analogy that
Oh, you mean with the fluids?
No, with the dual gauge state.
Okay. Yes. Yeah.
Your Hamiltonian or your system there is a quantum field theory of U1 gauge field and a complex scalar field, and it's in a thermal bath. The thermal bath is the temperature of the thermal bath is given by the temperature of the black hole.
Yeah.
So what is so now there's a critical temperature. So how are you measuring how are you saying that you are above and below the critical temperature? Is that given by the mass of the scalar field in the dual picture? If the mass is, if I'm sitting at the critical point temperature,
Yes.
how do I know I'm sitting at the critical temperature in the gravitational setting? I have a black hole.
Yes.
I have a temperature for the black hole that's set by ambient temperature. I understand that in the dual picture.
Yeah.
That's just the temperature that I put my quantum field theory as.
You have a thermal, and yeah, if you're sitting precisely at the critical temperature, the quasinormal mode sits precisely at the origin of the complex frequency plane.
So that presumably means that there must be a massless. Since
Yes.
you were
Yes.
analyzing
Yes.
modes of the scalar field,
Yeah. There will be a Goldstone boson.
but it is determined by the mass of the of your scalar field. You wrote down a scalar
Yes.
field with a mass.
Yes.
If that mass goes to zero, I presume I'm sitting right at the critical point.
No. No. So the easiest way to see the holographic superconductor picture is, so if you zoom in the near horizon region, so you have an ADS
Yes.
2,
Yes, I should. I mean,
Yes.
the dual picture should only correspond to the near horizon.
yes, so there you need to have a tachyon. So you need to violate the ADS2 BF band. So if the mass of your scalar field is 0, you don't.
Yeah, but that's the critical point.
Yes.
That should be the critical point.
No.
It's not. Or maybe there must be some relation between the mass of the scalar field and the temperature of the black hole for me to sit at the critical value.
Yeah. Yes. So usually we just
suppose I should figure out from an expectation value of infinity on the
so the expectation of the scalar field at infinity will tell you whether you have a condensate or not.
Exactly.
So that will tell you whether you are in the normal phase or the superconductor phase.
So I can detect it from the
Oh,
presence
yes,
of the
yeah.
current and say it.
Yeah.
But I was hoping to
Yeah,
get slightly more direct.
assuming that you are always on the thermodynamically preferred phase. Yes.
Yeah, if I
Yeah.
got you.
Yes. Yeah.
High temperature
Yes.
phase, I can reduce the mass of my black hole until it.
Yeah, it will slowly now, yes.
Where the condensate, when the instability will set in. Okay, but you're saying you can't read it off exactly from the mass of the scalar field, which is the only parameter
No.
other than that.
Any other questions?
I don't know a whole lot about the context of black holes, but I know in microwave quantum physics, people sometimes look at non-emission Hamiltonians, and often there's interesting behavior around what they call exceptional points. So these are points where you have these non-orthogonal eigenvectors, but they can coalesce into the same eigenvector. So I'm wondering if you saw anything like this happening in your system, or if it arises.
No. But I know that in quantum mechanics, people have tried to explore the implications of non-normality. So it's not just fluids.
Yes.
Just I'm not terribly familiar with that literature.
All the questions, we should just.
You were asking questions, so I didn't bore you.